All right, example 6. With this example, we're going to do a proof, and we are going to prove how to find the derivative of a to the x. Okay, so a is a constant, so we're going to prove how to find the derivative of things like 7 to the x. Okay, it's an exponential function because you have a variable in the exponent. So we'll be able to take it's any number raised to the x power. So we're going to prove how to do it, and then after we prove it, we'll talk about the rules, and then you guys can use the rule. It's just important that you guys see a few proofs as you go through this class, because if you go on in math, you'll have to do more proofs, so it's kind of something to preview and kind of get a feeling for it. Okay, so the top part is telling us a piece of information that will be useful in our proof. It says, recall from our work with exponential and logs that a is equal to e to the ln of a. This is true because e and ln would cancel each other out or simplify to 1 because they're inverses, and you'd be just left with a. Okay, so that would mean that if I wanted to do a to the x, I could take both to the x power on both sides, and you would see that we have this result here. Okay, the reason we're going to do this is because I want to find the derivative of a to the x, and this piece of information will help us out. Okay, so first thing we're going to do is simplify. Well, not simplify. We're going to substitute. Who's equivalent to a to the x? This piece right here. So it's e ln of a all raised to the x power. Okay, and now I really have a power to a power. And so in order to do a power to a power, I can multiply those two. So I really have e to the ln of a times x. And I have to write the d over dx. It's telling me to take the derivative because I actually haven't taken the derivative yet. And so now I'm actually going to go ahead and take the derivative. This would be a chain rule, okay? Because it's not just e to the x, it's e to the ln of a times x. Before we go ahead and take that chain rule, something I want to talk about is ln of a times x. A is a number, okay? So ln of some number is actually a constant. Okay, so it's like 5, it's like 7, it's like 12. Okay, it's a number. And if I were to take the derivative of 12x, I would just be left with 12. So if I were to take the derivative of ln of ax, the derivative of x is 1, so I'd be just left with ln of a. Okay, so something to keep in mind as we move forward. So let's chain rule this though. My inside is right here, and then e is my outside. So take the derivative. We do the derivative of our outside. E is our favorite derivative to take because the derivative of e to the x is e to the x. So it's e with our original inside plugged back in, ln of ax, times the derivative of my inside, which we just talked about. Ln of a is a constant, and then we have x. The derivative of x is 1. So times ln of a. And now from here, what I'm going to go ahead and do is simplify. Okay, this part right here, I'm going to rewrite it back as a power to a power. So I can really write this as e to the ln of a, all raised to the x power, and then times ln of a. We already talked about this as well. E to the ln of a, that simplifies to just a. So I have a to the x times ln of a. Okay, so this gives me my new derivative rule that a to the x is equal to a to the x ln of a, which we have written here. So for instance, if I asked you guys to take the derivative of 10 to the x. 10 is our a, so the derivative is 10 to the x ln of 10. If I asked you to take the derivative of, so it should be right here, 205x, it would be 205x ln of 205. Okay. So that is our new derivative rule. And that's where it comes from. That little bit of proof kind of shows you where the derivative rule comes from. So now that we've proved it, we can use this, and we'll try using it in our next few examples.